Good morning. This is Unit 6, Day 1 notes, and we're going to go over Introduction to Experimental and Theoretical Probability today. So, first of all, what is probability? Probability is the chance or likelihood of the event occurring. Okay, well, all events can be assigned the probability from 0 to 1. 0 means it's impossible for it to occur. We have like a 0.5 or 1/2 means that it's equally likely to occur and not to occur. And then number 1 would be certain to occur. So this is less likely. 0 to 1/2 is less likely. To occur. And then we have more likely to occur on this side. Well, we can base this on two things. Either it is based on experimental probability, observing results of an experiment, or we have theoretical probability. Using arguments of symmetry, logic, or math. Experimental probability, let's do an example. So I just had to read this. A small plastic cone was tossed into the air 279 times. It fell on its side 183 times, so the side is 183, and on its base 96 times. So the trial is the total number of times we flip or toss this cone, and the total number of times is 279. The outcomes are going to be the possible results. So different results possible for one trial of the experiment. We only have two outcomes. The outcomes are going to be either it's going to land on the side or base. The frequency is the number of times per outcome. So it looks like there was 183 for side. And then we have 96 for base. And then this one might be new to you. This is called the relative frequency. The relative frequency is the outcome expressed as a fraction out of the total number of trials. So the side would be something like 183 over 279, which is about 0.656% or 65%. And let's put a semicolon. The 96 out of the base over the 279 was about 34% or 0.344. I'm not sure what this box is. Go ahead and flip your paper over. The theoretical probability is going to be using math or logic. So we're going to use logic or math. And this is the formula. We kind of use P, or for the theoretical probability, is the number of outcomes of E, whatever E is, your experiment, divided by the total number of outcomes. So the number of outcomes of E divided by the total. So like the likelihood. The sample space is a set of all possible outcomes of an experiment. Three different ways to illustrate the sample space. So listing the outcomes of tossing a coin. Those are three different ways to illustrate sample space of tossing a coin. So we can use just list the outcomes. We can use a two-dimensional grid. So if I want to list the outcomes, my sample space is, if I have two coins, I'm going to use 2 coins on both. 2 coins. I could have had heads and heads. I can have, let me just put I can have a heads and tails. I can have a tails and heads. And I can have a tails and tails. This is my sample space. If I am rolling a die, I can have a 1, a 2, a 3, a 4, a 5, or a 6. This is my sample space. Two-dimensional grid involves 2 events. So when we are talking about tossing a coin, I'm going to make this my heads, and this is my tails, and I'm going to make this my heads, and this is my tails. It's possible for there to be both heads, 1 heads, 1 tails, 1 tails, 1 heads, and 2 tails. So this is maybe the first coin. I'll label my axes, and then this is my second. I'm going to move on to a tree diagram. Draw 2 marbles from a bag containing a red, green, yellow marble with replacement. So each time we're putting them back in. What we have to remember is the last branch represents the total outcomes. So if we are drawing marbles from this bag, red, green, and yellow, my first one, I have 3 options. I can, either draw a red marble, a green marble, or a yellow marble. And since that's why we're going to replace it, put that red one back in, I can now draw a red, again, a yellow, oops, I forgot green, green. Again, after I put that green back in, I can now draw a red, yellow, or green. And then if I put that yellow back in, I can now draw again a red, a yellow, or a green marble. So this one says a ticket is randomly selected from a basket containing 3 green, 4 yellow, and 5 blue tickets. So we got to add these up. I think the total is 12. What is the probability of getting a green ticket? So the probability of a green is 3 over 12. And you can simplify this. This is 1/4, 1 to 4, or 25% or 0.25. An orange ticket, this is a time, this is O for orange, not 0. To get an orange ticket, this is going to be a time when this is not likely. If there's no orange tickets, then we can't get one. Probability of green or yellow. So the mathematical or is the inclusive or, and this means and it means or. So we can actually have both. So we're going to have green is 3 and yellow is 4. So this is 7 over 12. I don't think you can simplify this. Maybe make it a um, decimal. Probability of green or yellow. Green, yellow, or blue, we're going to add them all up, and that equals 1. The probability, if you're going to pick one, then we're going to have one of these. So it's almost guaranteed you're going to get one of those. Complementary events are exactly one one of the events must occur. If E is an event, then E prime is the complement of event E. Okay, so the probability of E plus the probability of the complement of E prime, is equal to 1. It's guaranteed. A marble is randomly selected from a box containing 5 green, 3 red, 7 blue marbles. This total is 15. Yeah, equals 15. So the probability of red is 1, 3 over 15, or 1 over 5. The probability of not getting red would be the probability of not red would be 1 minus 1 over 5, or this is equal to 4 over 5. Alrighty, let's just do this last one. Red or blue. Let's do blue. Probability of red or blue is red is 3, blue is 7. That's 10 over 15 is 10 over 15, or let's simplify that. It's equal to 2 over 3. Now, neither red nor blue, then this is the probability of red or blue prime, which is equal to 1 minus 2 over 3, which is 1 over 3. It says from this grid, we've already talked about this. We know that use two-row dimensional grid to illustrate the sample space for tossing a coin and rolling a dice simultaneously. So let's actually go over this one. So if we're tossing a coin, this one's smaller, I'm going to put it here. We can either have a heads or a tails. Oops. Tails. But if we're rolling a die, we can get 1, 2, 3, 4, 5, or 6. And these are all of these are all of the outcomes. We can have a head and a 1, a tails and a 1, a head and a 1, a 2, 3 can be a heads or a tails, 4 can be a heads or a tails, 5 can be a heads or a tails, and 6 can be a heads or a tails. So there's like a dash line going this way, and we have vertical lines going on each of these dice. So my total probability for tossing a heads is going to be, if there are 12 outcomes, there's 6 of them, so 1/2. Probability of getting a tail and a 5, so a tail and a 5 are right here. But, so that's going to be a 1 out of 12. Probability of getting a tail or a 5. So I can have a tail or a 5. And a tail can go this way, right? Or a 5. So if there's 12 possible, it looks like there are 1, 2, 3, 4, 5, 6, plus 1 is 7. 7 over 12. I want you guys to try the rest. And if you have any questions, let me know. I just want to give you this formula for independent events occur. Events where the occurrence of one event does not affect the occurrence of the other. So does not, maybe, or doesn't affect the occurrence of the other event. If A and B are independent events, this is a very important formula. So probability of A and B is going to be the probability of A times the probability of B. If A, B, and C are all independent events, then we have the probability of A times the probability of B times the probability of C. Okay, so let's keep going. It says they have 2 photocopiers in one day. Machine A is at 8%, chance of malfunctioning. Machine B is at 12%. They don't have anything to do with one another. So determine the probability that any one day they both will malfunction. Well, the probability of A and B is the probability of A times the probability of B. And the probability of A is, we have to move that decimal spot over twice. So it's going to be 0.08 times probability B. You had to move that decimal spot over, so it's going to be 0.12. And I think this is equal to 0.0096. Okay, work effectively. Well, if there's 8% chance that they're going to malfunction, then that means that there's a 92% chance that it's going to work, right? And if there's a 12% chance that this one is going to malfunction, then that means that there's an 88% chance that it's going to work. So working effectively is the complement of not working. So the probability of the complement of A and the complement of B is the probability of the complement of A times the probability of the complement of B, or the opposite of B. So we actually have to subtract them from one individually, and then we're going to multiply them. So this is a 0.92%, or 0.92 times the probability of B, which is a 0.88, which is about an 80%, or 0.8096 of working effectively. But these two are not complements of each other. Okay, that's very important. This is going to be the last one I'm going to try the rest, and ask me if you have any questions. Have a wonderful day.